compound inequalities. In this presentation, we'll be talking about solving them, graphing the answer on a number line, using that information to write it as interval notation. In a bonus section, we'll talk about intersection and union with sets. Welcome to Mark's Math Methods. But first, a little refresher. Let's take this inequality. X is greater than 3. Well, the only number I have is 3, so if I graph it on a number line, I have a 3. I need greater than, that would be to the right. And because 3 is not included, I use a parentheses. X is less than 3. So again, I have 3. I want less than, so those are to the left. And because the 3 is not included, I use parentheses. Back in the old days, we used open circles, but now we use parentheses. X greater than or equal to 3. So I have 3 again. Greater than means shading to the right, but in this case, 3 is included, so I use a bracket. X less than or equal to 3. Again, 3. Less than is to the left, and it's equal to, so the 3 is included, I use a bracket. Back in the old days, they would have used a closed circle. Interval notation is talking about the shaded area. It's a shorthand notation for the shaded area. It has two parts: the left edge of the shaded region and the right edge of the shaded region. And then, of course, it's surrounded by parentheses or brackets, depending on whether it's an equals component at that number. Note infinities, arrows on the graph, always get parentheses. So let's take a look at the first one. X is greater than 3. The left edge of the shaded area would be 3. The right edge of the shaded area would be an arrow, so that's an positive infinity. The infinity always gets parentheses, as well as the fact that the shaded area on the left does not include the 3. So it gets parentheses. Second one, X is less than 3. The left edge of the shaded area is an arrow. That's negative infinity. The right edge of the shaded area is 3. Infinity always gets parentheses, and the 3 is not included, so it also gets parentheses. X is greater than or equal to 3. The left edge of the shaded area is 3. The right edge of the shaded area is the arrow. That's positive infinity. Because the 3 is included, it gets a bracket. The infinity always gets parentheses. X is less than or equal to 3. The left edge of the shaded area is the arrow on the left, or negative infinity. The right edge of the shaded area is 3. Infinity always gets parentheses, and because the 3 is included, it gets a bracket. So this is a compound inequality. It says -5 less than 2x minus 9 less than or equal to 3. Because it's compound, it means it has two parts. Okay, if we look at the part on the left, which says -5 is less than 2x minus 9, that's one part. The other part would be the right side. 2x minus 9 is less than or equal to 3. So what would you do to solve the one on the left? Well, you would have to add the 9 and then divide by 2. What would you do to solve the one on the right? Well, I'm going to add the 9 over, and then I'm going to divide by 2. Wow, it's the same procedure. So let's solve this compound inequality. So we're going to add 9 not to both sides, but to all sides. Since there are 3 pieces, we have to do it to all 3 parts. So we're adding 9 to all 3 parts. Negative 5 plus 9 is 4. 2x minus 9 plus 9 is just 2x. And 3 plus 9 is 12. Notice the symbols came straight down. Now we're going to divide not both sides, but all sides by 2. 4 divided by 2 is 2. 2x divided by 2 is x, and 12 divided by 2 is 6. So there's our solution. 2 is less than x, which is less than or equal to 6. Now we're going to graph it. Well, the only numbers I have are 2 and 6. So I'm going to plot 2 and 6. Now if I looked at the left-hand side, think of it as 2 is less than x, or I need the x's that are greater than 2. So I'm going to shade it to the right from the 2. If I look at the other side, I need x's that are less than or equal to 6. So I'm shading x's that are less than 6, shading to the left from the 6. There is no equals component at the 2, so it gets parentheses. There is an equals component at the 6, so it gets a bracket. So there's my graph. That graphs the solution of 2 less than x less than or equal to 6. Now I write the interval notation. Well, the left edge of the shaded area is 2. The right edge of the shaded area is 6. On the graph at the 2, I have a parentheses. On the graph at the 6, I have a bracket. And therefore, that is interval notation. So I solved it, I graphed it, and I wrote the interval notation. Some people can go directly from the solution to the interval notation. I prefer to go through the graph, because once I've plotted it, it's so easy to grab it off the graph to interval notation. So let's try this one. 7 is greater than or equal to negative 3z plus 7 is greater than negative 5. So I'm going to subtract 7 from all sides. So I get 0 is greater than or equal to negative 3z is greater than negative 12. And now I'm going to divide all sides by negative 3. So I get 0 is less than or equal to z, which is less than 4. Did you notice that the inequalities switch directions? The one on the left greater than or equal to became less than or equal to, and the one on the right greater than became less than. And you're saying, why? Well, when I inserted a negative for multiplication and division purposes, that 3 I put down there was a negative 3. That forces me to change the direction of my inequality symbols. Never had to do that with equal signs, because when you flip an equal sign, it doesn't make a difference. But when you flip an inequality symbol, it does make a difference. So there's our solution. 0 less than or equal to z less than 4. So if I graph it, the only numbers I have are 0 and 4. When I look at the left-hand side, I need zeros that are less than z, or z's that are greater than 0. And on the right-hand side, I need z's that are less than 4. So I'm going to shade to the left from the 4. I have an equals component at the 0, so I get a bracket. I do not have an equals component at the 4, so it gets parentheses. Interval notation, left edge is 0, right edge is 4. The 0 from the graph you can clearly see gets a bracket, and from the graph the 4 gets parentheses. So there's our interval notation. We have a solution, we have a graph, and we have interval notation. The only tricky thing here was because I inserted a negative number for division or multiplication purposes, when I divided by -3, it forced me to change the direction of my inequalities. Sometimes a compound inequality is written with the words and or. In other words, it's not actually written together as a single inequality. They write it as two pieces, but they use the word and or. And represents intersection, where the pieces meet. Such as x plus 6 is greater than or equal to 8, and x plus 5 is less than or equal to 9. So because I'm using the and, it's an intersection. Or I like to say it's an intersection, because the symbol sort of looks like an N. So it's an intersection, and intersection. The or is represented by the U for union symbol. It's just like a bucket. You throw it all in the bucket. So negative 5x greater than 20, or x plus 5 is greater than or equal to 3. Because we're using the or, it's a union, so it's going to be everything. So let's look at a couple of these, one each. And occasionally they want you to write it in set builder notation. So let's look at that first one. Here it is in set builder notation. It says the set of all x's such that x plus 6 is greater than 8 and x plus 5 is greater than or equal to 9. So let's look at the two pieces individually and solve them just like we did before. So if I subtract 6 on the left, I get x is greater than 2. If I subtract 5 on the right, I get x is less than or equal to 4. So when it comes to and or ors, what I like to do is I'm going to graph three things. I'm going to graph the top one on the left, one on the top. I'm going to graph the right one in the middle, and the bottom will be my answer. So I need to make sure that I put the 2 and the 4 in the appropriate orientation. So x is greater than or equal to 2, equation 1, would look like that if for the shaded area. And because it is an equals component, it gets a bracket. Equation 2, because the 4 is farther to the right on the number line than the 2, I had to put it on the right. So I do need to understand how those numbers are related before I do anything. So I need x's that are less than or equal to 4. So I'm shading to the left, and it gets a bracket. Now, the bottom one here is the graph of the intersection, because it's an and, it's an intersection. So I need to put where the two graphs meet. So I'm going to draw a little dotted line at each number. On the left-hand side, they don't meet. There's only one there. In the middle, and on the right-hand side, they don't meet either. There's only one there. But in the middle, the two graphs meet. So that is my solution. That's the graph of the intersection. And of course, at the 2, it has a bracket. And also at the 4, it has a bracket. So that would be the graph of the solution to this intersection question. And if I wrote it in interval notation, pretty straightforward once you get the graph. The left edge is 2, the right edge is 4, The left edge gets a bracket and the right edge gets a bracket. So I first solve the two pieces individually. X is greater than or equal to 2, X is less than or equal to 4. I graph equation 1 on the top. I graph equation 2 in the middle. And then because this is an intersection where they meet, which is in the middle section, the left section and the right section only have 1. Now let's try an OR. Again, I want to solve the pieces individually. So when I divide by -5, I get X is less than -4. And when I subtract 5 from the one on the right, I get X is greater than or equal to -2. So let's look at the graph. Equation 1, X is less than or equal, or less than, sorry, to -4. It's going to go to the left. No equals component. Equation 2, X is greater than or equal to -2. So there's our graph. Now this is an OR, union, so I'm just going to throw it all in there. So I have a piece here, I have a piece here, and I get the brackets and parentheses. So there is the solution as a graph. It's got two distinct parts. So when I do the interval notation, I've got a left piece, which has a left edge of -infinity and a right edge of -4. I've also got a right shaded area, which has a left edge of -2 and a right edge of +infinity, bracket and parentheses. But because I've got two distinct pieces, I'm going to put the union symbol between them, because it could be either part. So I put the union symbol between them. Let's talk about intersection and union of sets. So let's let set A be 1, 3, 5, 7, and 9, and set B 1, 2, 3, 4, 5. So these are not equations. These are specific values in set A and set B. They're not inequalities. They are specific groups of numbers or items. It doesn't have to be numbers. So let's set C equal to the intersection, it's like an N, intersection of sets A and B. Well, that means where do they meet? Where do the two sets meet? What is in both sets? So set C, well, if I look at part A and B, they both have a 1. They both have a 3. And they both have a 5. So there's my set. Set C is 1, 3, and 5. Now let's let set D equal the union of A and B. In other words, it's a bucket. We're going to throw it all in there. Anything that's in anything gets used. We're going to throw it all in the bucket. So if I grab from set A, I get all of those. Spread them out. Now if I grab from set B, I get all of those. The ones that repeat, I don't need to list twice. So I've just got 1, 3, 5, 7, 9 from A, and I get to add to it 2 and 4. So it's 1, 2, 3, 4, 5, 7, and 9 would be the union. So that's doing sets as opposed to inequalities. I hope the presentation was helpful. Thumbs up, subscribe, comment. And if you have any problem types you'd like me to demonstrate, there's my address.